Good morning, students. Today we will discussing about the from solution chapter. From solution chapter, Raoult's law as a special case of Henry's law. Raoult's law as a special case of Henry's law. So we know already what is the Raoult's law for volatile solutions. So according to Raoult's law, Pi equal to Xi Pi naught. Pi naught. So this is partial vapor pressure of component I component, and this is mole fraction of I component. This is partial vapor pressure of in pure state component in pure state. So this is according to Raoult's law. Here Pi naught is proportionality constant. So proportionality constant equal to vapor pressure of solvent, vapor pressure of pure components. So when we know we'll see the Henry's law, P equal to KHX. So partial pressure directly proportional to the mole fraction of the solid in the solution. So here KH equal to KH is a proportionality constant. KH is a Henry constant, proportionality constant. So here Pi naught equal to KH. All are equal, but only differences here. KH differ from the Pi naught. So that means what here? When comparing mutually here, KH is a equal to the Pi naught. Means vapor pressure of pure in state of the component. So that's why we can call Raoult's law as a special case of Henry's law. Then another thing is 2.4. Another subtopic is vapor pressure of solutions of solids in liquids. Vapor pressure of solutions of solids in liquids. So generally the liquid solutions two types, that is solid in this discussing in this chapter, two types of liquid solutions, that is gas in liquid solutions and solid in liquid solutions. Another one is liquid in liquid solutions. So liquid in liquid solutions, solid in liquid solutions. So in previous class we know what is the liquid in liquid solutions, vapor pressure of liquid in liquid solutions. What happens is there. Now today in this video we are discussing about the vapor pressure of solutions of solids in liquids. Then here generally solid in liquid solutions that containing components are here solid dissolved in liquid. Solid in liquid solutions mean what? Solid dissolved in a liquid. For example, sodium chloride, glucose, urea, cane sugar, all these dissolved in water. So sodium chloride, glucose, urea, cane sugar, like that, dissolved in water. Dissolved in water. Another some examples: iodine, sulfur, acid. These are dissolved in CS2. CS2, carbon disulfide. Carbon disulfide. So when we know this, when we see in this that the physical properties of these solutions, are quite different from those of pure solvents. From those of pure solvents, different from those of pure solvents. So different. So some difference are there. So that's why the physical properties quite different. Physical properties of the solutions quite different from those of pure solvents. So for example, we will take two vessels, in closed vessel, two vessels. One is only one in one vessel. This is A and this is B. In A vessel only this containing only pure solvent. So this solvent may be volatile. So what happened in this? So the surface of the molecule of pure solvent. So easily escape from the surface and that converted into gaseous state. Or vapor phase or vapor state. So that's why after equilibrium conditions under particular given conditions, temperature and pressure, that may be existed a dynamic equilibrium from the surface of the molecules, escape from the surface of the liquid, then from the surface escape from this one and goes into the vapor phase. This is vapor phase. Suppose in vapor phase the number of molecules of pure solvent in vapor phase may be here 8. 1, 2, 3, 4, 5, 6, 7, 8. So 8 molecules. Let us consider here 8 particles in vapor phase. Why this going into this one? Why is for example this one? Why it is means that is this tendency of the molecules of the surface of the molecule, they have a more energy. So that's why that will be ready to escaping from the surface of the liquid. And converted into vapor phase. So that's why all these surface of the molecules ready to convert it into this side. So means in vapor phase. And similarly when we take B, so equimolar of solution means solid and solvent both are equal molar means 1 mole of solid and 1 mole of solvent. When we taken in the vessel B, so what happened that the surface of the liquid occupy the molecules solvent and solid. So what happened is this is maybe non-volatile. Here solid is a non-volatile. What happened maybe this is not escaping from this. So that's why only here volatile solvent can escape from the surface of the liquid. So overcome the attraction forces of liquid and then getting some escaping from this. So in some of the going into the vapor state. So in this vapor state, how many? Only four molecules are present in this one. So why? Because here, why? Because the number of surface of the liquid, number of pure solvent molecules only decreases on the surface of the liquid. So here only this is only all are solvent molecules surface of the liquid, but here solvent and solid molecules are there. So that's why here a little bit somewhat comparatively this one, this is decreases. So that's why, for example, we have to take the vapor pressure. Why? Because here physical properties of these solutions are quite different from those of pure solvents. For example, here we take vapor pressure. What happens here? When comparatively pure solvent, this solutions has lower vapor pressure. So the decrease in the vapor pressure of solvent depends on quantity of non-volatile solute in the solution. Depends on quantity of non-volatile solute in solution. So the decrease in the vapor pressure of the solvent depend on what? Which one depend this one? So non-volatile solid, quantity of the non-volatile solution irrespective of its nature. So for example, here decrease in vapor pressure of water by adding 1 mole of sucrose in 1 kg of water. 1 mole of sucrose in 1 mole of sucrose in 1 kg of water. In 1 kg of water, or 1 mole of glucose in 1 kg of water, or 1 mole of NaCl in 1 kg of water, whatever it may be. So here only depending the vapor pressure, decreasing vapor pressure, that is depend on the quantity of the non-volatile solid, and not nature of and not its nature. So that's why according to Raoult's law, in general for any solutions the partial pressure of the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. Partial vapor pressure of each volatile component in the solution directly proportional to the its mole fraction. So this is a Raoult's law for any solution. In general, this is a Raoult's law. In general, Raoult's law, the partial vapor pressure of each volatile component in the solution directly proportional to its mole fraction. In the solutions. So according to Raoult's law, so let us consider a binary solution. Let us consider in a binary solution. binary binary solution. Binary solution. Binary solutions means what? Two components present in the solution. Two components present in the solution. So component 1 is a solvent. Component 1 is a solvent and component 2 is a solid. Component 2 is a solid. In a binary solution, denoted component 1 is a solvent. Another one is component 2 is a solid. Component 2 is a solid. So we can denote the vapor pressure of one P1, that is vapor pressure of solvent. Here P1 means vapor pressure of solvent. And X1 means mole fraction of solvent. X1 is a mole fraction of solvent. And P1 naught is a vapor pressure in pure state. Vapor pressure in pure state. According to Raoult's law, partial vapor pressure of each component directly proportional to, according to Raoult's law, P1 equal to X1 P1 naught. This is a for in a binary solution will consider the partial pressure 1 equal to vapor pressure of the component 1 equal to X1 P1 naught. So this is the for binary solutions when present in non-volatile solid. Then here we draw the graph between vapor pressure and mole fraction. Vapor pressure and mole fraction of the solvent. This is vapor pressure and this is mole fraction, and that gives what? A straight line or linearly. Up to when it is touching the pure state. Here this is the pure state. Vapor pressure up to increases up to the partial vapor pressure of each for solvent increases up to reaching the pure solvent. So this is X equal to 0 and here X1 equal to X1 this is 0, here 0, this is 1, means X1 equal to 1. This is vapor pressure and this is mole fraction. So this is vapor pressure of pure solvent or pure solvent. So this is vapor pressure daily increases up to the its pure state, P1 pure state. Then so this is when draw the plot between mole fraction and vapor pressure. So this is the vapor pressure of solutions of solids in